King Abdullah University of Science and Technology. Before joining King Abdullah University, Professor Hussein worked for ConocoPhillips and Chevron companies for about 12 years, where he conducted projects related to chemical enhanced oil recovery, carbon dioxide enhanced oil recovery, steam flood, EM heating, and others. Professor Hussein currently his research includes chemical enhanced oil recovery, geological carbon dioxide storage, data-driven modeling, and reservoir simulation development. Professor Hussein earned several SPE awards, including SPE Distinguished Lecturer in 2009, and served as Associate Editor for SPE Journal for more than 10 years. Please welcome Professor Hussein. Thank you so much for joining, and over to you.
Great, thank you very much, Amina. Can you hear me well?
Yes, we can hear you well.
All right, excellent. And thank you for this invitation, especially for SPE, student chapter, University of Bahrain. This is a great pleasure for me to be here and to share with you some of our work related to chemical EOR. So I'll start with first I'll give an intro about the enhanced oil recovery. Maybe I'm gonna cover some of the basics of this technology just to set the ground for everybody, since I don't know really what's the background of all the audience. Then I will talk more specifically about Polymer Flood. It's not gonna be very technical in terms of like showing equations or so, but I'm gonna talk about some of the challenges in this technology and the potential, and then I will generalize, with the giving some lesson learned, from field applications, field trials, and essentially what's the takeaway from this presentation. All right, so this is let me start with what we call the oil field production life cycle, and most likely you're all familiar with this. That we typically start with what we call the primary recovery, where you just drill wells, mainly producers, and you rely on the reservoir, energy and pressure to push the oil up to the surface. This technology will give you maybe, let's say, about 15% in terms of recovery factor on average. And then once the pressure really, depletes and go down, we need to do a bit more actually to produce the oil out. So one of the very common technologies here is that we use water flood. So in this case now we need to have injectors besides the producer where water is injected to displace oil to the other side. So from one side we maintain the pressure, the other side we have some displacement force that will help the oil to get out of the system. And with this technology, you can get maybe about 40% recovery factor for it. Now, which is, again, could be the most common technology right now, all right, in the industry. Now, at some point where you start actually to get water recycled back, breakthrough of water, and then this efficiency, the efficiency of this technology drops, we need to do something more, to improve the efficiency. In this case, we get to what we call enhanced oil recovery. So with enhanced oil recovery, EOR, typically we need to use fluids that beyond or outside the in-situ fluids in the reservoir. So in this case, we may use chemicals, you may use gases, and so on. So this is the part that we're gonna talk a bit more about. And with this technology, you can push recovery factor beyond 40%. You can maybe reach 60% or even sometimes more than that. All right, so why do you need EOR? How does the EOR work? Why it is more efficient or can improve the efficiency of water flood? Well, there's two aspects to it. From one side, EOR method can increase what we call the sweep efficiency. This happens at the macroscopic scale. So in the reservoir, when we inject water may not be accessible everywhere. It may not reach all the corners, if you like, in the reservoir. So some spots will be bypassed by water, and this is what we call the bypass oil. Now, even if you look at the areas that may get flooded with water here, it doesn't mean that all the oil gets swept, okay, from that zone, because some of the oil will stay behind and trapped at the pore scale. And this is related to the wettability of the rock, related to the pore structure and the capillary forces in it. And this is what we refer to as the microscopic heterogeneity or effect. Now, EOR method can help in both sides, can help actually to improve the sweep efficiency, like in the case of polymers, and can help in improving the sweep efficiency, like the case of surfactants or miscible gases and so on. All right, so what are the EOR methods? There's really different methods out there. One classification of this method is, I use three classes of this method. One, what we call the water-based EOR. So in this case, the main, if you like, fluid is water, but we add additives to it. So in this case, for chemical EOR, we use polymers. We're going to talk about them. We use surfactants and other chemicals. There's also the microbial EOR and low salinity, where we change the chemistry of the water. There is the gas-based EOR methods. In this case, we use miscible gases like CO2, hydrocarbon-based gases, and so on. There's also slightly miscible or immiscible gases like nitrogen and so on. There is combination of the two, like the WAG, and also sometimes we even add more chemicals to it to create foam, okay, for it. But this is the gas-based. Both classes here are non-thermal methods. So essentially, we're not adding energy or heat to the reservoir, versus the other class, which is the thermal EOR, where we add energy in terms of heat. In this case, we use like steam drive, for example, and the variety of these methods like CCS, SAGD. Even some cases we use air injection, where actually we create what we call the in-situ combustion. So this is just to give you a briefly about these different types of methods. Now, in terms of maturity of these methods, this is a chart by Professor Gary Popp from UT Austin, and he showed this really very nice way to show these different methods, EOR methods, in terms of maturity and versus time. So the higher here on the chart, the more mature methods. And you see here, also reflects the more applicable methods right now. You see here on the top of the chart, you see steam, miscible gas. So miscible gas is essentially CO2 flood, thermal gas, SAGD, polymer, low salinity. So this goes to the top, or the most used or most mature methods right now, and goes down on the chart, right? I'm not gonna go all the way to the different methods, but as you see here, there's really a variety of these methods. Now, where do you use this method? They are not applicable everywhere, right? So steam doesn't work everywhere. There is specific conditions or specific preferred prerequisites for this method to work efficiently. And this is a chart also by the same author that shows here what are, for instance, if you use, let's say, CO2, all right, what would be the preferred conditions for the oil or for the reservoir? You can see here that we prefer that the oil to be, somehow like light oil or not very heavy oil, the API gravity above 22, viscosity below 10 centipoise, depth below 2,000 feet here, and so on, right? And this is, these are sort of what we call the screening criteria. They are not solid criteria, meaning that, there's some exceptions to this table, but this is where just based on field observation, field experience, these are the most common conditions to make this specific technology successful here. And it goes for CO2, nitrogen, steam, SAGD, polymers, and so on. All right, for it. All right, now in terms of EOR contribution worldwide, this is shows you sort of the big picture. Where's EOR, which EOR method and where are they used? You can see here some, sorting by country in terms of contribution in barrels per day coming from EOR methods. You see United States on the top, China, Canada, and so on, right, on it. And here you can also see the methods that are used, all right? So in the US in red, you see it is thermal methods. So again, thermal, essentially using steam or hot water. You see, here in the dark yellow here, you have the gas, essentially. So you have gas, meaning that the immiscible CO2 or nitrogen. And then you see also CO2 here has significant, proportion of the contribution. And so on, chemicals little bit in the US, while it has more in China and so on. And this is the overall contribution. You see here in red is thermal, CO2, and then green in chemicals. And this is essentially what, floated on the top of the charts with Gary Bob's chart there. Now, in terms of projects, there's currently around 375 EOR projects worldwide operational, produce about 2% of, or contribute about 2% of global oil production. So if you say roughly 100 million barrels per day production, currently 2% is about 2 million barrels per day. All right, and this is also another outlook from IEA, shows the different EOR methods. You can see here over time the contribution of EOR methods. 2020 we're here, yes, we're around 2 million barrels as you see here. And this is the outlook where the EOR method will maybe contribution in the future. You can see that even up within 2040, the contribution maybe will be within the 4 million barrels per day, which is still very modest, okay, for EOR methods. Now, what's contributing to this? Why EOR method is not extensively used, worldwide? There's many challenges to it, right? And I'll talk about some of them here. So EOR challenges, starting with the high cost and risk, all right? This very costly technology and high risk, meaning that it's not really mature compared to other technologies. And this reflects on the return on investment, right? There's risk there. Low incentives. Well, here depends where you are. Like in some places like the US, if you implement or deploy EOR method, you may get tax incentives, for example. Like for chemicals or even for CO2, mainly for CO2 right now, you can get tax incentives. Same actually in some European countries. But other countries, they may not have any incentives if you apply an EOR method. EOR also, there's many other methods, like especially water flood. It is very competitive, so which is much cheaper as well. So it is really hard to justify EOR method in many situations. Feasibility and deployment. This reflects that the prerequisites that I talked about. So EOR methods may not apply everywhere, right? You need to have really very careful and very specific conditions for this method to work. Also, you may have challenges of the availability of solvents and accessibility. Like, for example, if when I use CO2, where does CO2 will come from? You have a nearby source for CO2. Sometimes you need to have long pipelines to transport it and so on. Is it offshore or onshore or offshore? This makes also add complexity. And on top of that, you may also face regulations, country regulation, environmental footprint, public perceptions, and so on. So these are also other aspects to it. What's the value added of CO2? What's the value proposition, for EOR, okay? So on top of basic what the challenge is, right? From one side, there's benefits from EOR methods. This method can boost production rates, right? They can increase ultimate recovery factor from, let's say, 50th% with water flood and even, infill drilling and so on, can even boost it maybe to 60-70%. That's a possibility to do that. So in this case, it can create business opportunity. You may get access to some government incentives, like, for example, the 45Q tax credit in the US if you use CO2 for that. And for company, they build up reserves from R to R to P, which is resources to reserves to production, right? So you can increase the reserves of the company. Okay, so there's value from doing that. So these are the direct benefits from EOR methods. There's also could be indirect benefits. Like, for example, for national, provide national interest for NOC, national ore companies. For instance, it can safeguard the natural resources. It maximize, right, the productivity from your national resources and so on. Can provide energy independence, in-house capability, build and develop in-house capabilities and know-how. It's also strategic for IOC independent oil companies that it can provide competitive edge. And this is how companies compete, right? If a company wants to go and compete to get acquire assets, for example, in other places, they need to show that they are competitive, they have technology and so on. So it is even if they don't implement it, right? They need to show that they have the capability to do this type of high-tech technology, in this sense. It is important for the transition for decarbonization, and I'm pretty sure now you're hearing a lot about this, especially for CCUS, and this is by deploying CO2 EOR. Okay, and this is becoming very, it's gaining a lot of attention. And with that, you can have maybe licensing to keep oil flowing, right? The companies, they need to show, oil and gas companies, they need to show that they're doing something, right, to not only producing oil and gas, but also they're doing something to mitigate the current challenge of CO2 emission and global warming and so on. So this will be needed definitely, in the coming, it's already happening right now. And this could be provide job opportunity, boost the economy and so on, from service companies, from local providers and so on. So there is a lot of benefit of EOR methods, all right, besides that. Now let's be a bit more focused here and talk about Polymer Flood. All right, polymer could be the most used, it is the most used chemical EOR method. There's many projects out there worldwide. It is, relatively speaking, low risk, can provide a good incremental recovery factor in the range of 5 to 15%, can improve sweep efficiency, sometimes can also improve displacement efficiency. And these are some conditions, that the prerequisites that we need. So it operates at, or best works for low temperature reservoirs. That's below 200 degree Fahrenheit, so roughly 90 degrees C. It requires to have high remaining oil saturation in the reservoir, right? So if your reservoir is completely depleted, let's say, with remaining oil saturation below 40%, say, polymer will not work. Okay. It requires high KH, so K primarily H, the pay thickness, to provide enough injectivity. So you need to have injectivity in the range of, I would say, minimum 0.05 per volume or 0.1 per volume to be on the safe side. So you need to have very high injectivity in the reservoir. Okay. In other words, you need to inject 1 per volume within 10 years. Okay, for it. You need to inject at least 0.6 per volumes to be really effective, and reduce mobility ratio by a factor of 5. All right, to improve the efficiency of polymer. With polymer, you need also to have small well spacing compared to water flood. Okay, the residual time or residence time of polymer, it has to be within 6 months or so, maximum maybe 1 year. So in other words, the polymer molecule is not going to stay effective in the reservoir forever, right? It has sort of a shelf time, if you like, in the reservoir. Okay, otherwise, after that, start to degrade. And the oil viscosity, it has to be below 1,000 centipoise. So polymer doesn't work for very thick, very viscous reservoirs or oil. And in terms of efficiency, typical efficiency is within 1 to 10 pounds per barrel of incremental oil. So in other words, you need to use 1 pound of polymer to produce 1 barrel of oil. If you're 1 here, or 10 pounds to produce 1 barrel. Okay, so this is on the low efficiency side. So roughly speaking, 1 pound is about $1. Okay, for it. So in other words, for each incremental barrel, you need to use 10 pounds, $10 for it. Of course, with the current oil price, right, this is highly justified, right, for it. But again, here this is not the only cost, right, because you need to add on top of it, this is only the cost of the chemical, right? The more chemical you need put here, you need to have the higher capex as well, right? You have facilities, you need to have pipelines and so on, which is also you need to take into account. And also high polymer concentration typically leads to low injectivity that we're going to talk about. So probably you need also more wells and so on for it. All right, where's the benefit come from? The 5 to 15 incremental recovery. So when we say incremental recovery of polymer, we mean actually compared to the baseline water flood. So the baseline water flood is what we call the do-nothing case, or the water flood baseline here, the blue curve here reflecting the recovery factor. Typically, you see something like this. When polymer works, you need to see a kick in the production when you start to get the oil bank, and this will, boost recovery factor. There's two benefits from this. From one side, you can see here I have incremental recovery factor, and the other side here there is acceleration as well. So even meaning that if you continue water flood, it's going to take you more time to reach this recovery factor that you can achieve with shorter time with polymers. There's also it can help to reduce water cut. So on top of improving the recovery factor, typically polymer flood reduces the water cut. So meaning that you're going to have less costs associated with water handling and water recycling. And of course, it's more, meaning that it's more, environmental friendly compared to just water flood, by doing so. What are the typical polymers that we use? There's many synthetic polymers out there like HPAM, AMPS, AP, and so on. I'm not going to go too much in details on them. There's also biopolymers like xanthan gum. This is typically used like in jello or something in the food industry. Of course, this is not used anymore or very rarely used right now. We use more the synthetic polymers. They're less expensive. And so what we do here, this is the HPAM, for example. It comes as a powder. You dissolve it in water and it gives you viscosity, increments the viscosity. And with that, it provides what we call mobility control. So it reduces this mobility ratio, which is, as you see here, you have the viscosity of the oil divided by viscosity of the water. And as you increase this viscosity coming from polymer, you increase this number. And this number here from this experiment on the right here, typically this has the recovery factor. It is a function of the mobility ratio. So the low mobility ratio here, you see here, for example, M is 5, you find that recovery factor is 60% for this particular experiment. And if you would increase recovery factor, let's say to higher numbers, from 600 to 7,000, for example, recovery factor drops to 12%. So there is benefit in reducing the recovery factor by adding polymers, okay, for it. And this is what we try to do. Now let's talk a bit more about polymers. Okay, the HPAM are the most used polymers right now in the industry. So you can see here from some statistics where HPAMs here are 57 out of maybe like 65 or so. They are most used polymers. They are long, linear, long chain molecules, very heavy, right, from 2 to 20 million daltons here. Is this change commercially available at low cost? I mentioned, maybe it varies between say 0.5 and $1 per pound. The high viscosity yield. This is from a characteristic point of view, but they have limitations, right? Or the issues that we face with polymers. They're sensitive to temperature. So with high temperature, this long chain linear change tend to collapse, right? And as it collapses, meaning that its effectiveness on improving viscosity reduces. All right. Also, these polymers, they are sensitive to salinity and hardness, right? With high salinity, they have similar effect as the temperature. So also these chains, polymer molecules, they tend to shrink again, meaning that they're gonna be less effective in increasing the viscosity. They're subject to mechanical degradation, meaning that these, if you're not careful in handling these polymers, if you put them, for example, in very shearing mixing, you may break these molecules to smaller ones. And as you break them, also, this will reduce the viscosity of the fluid. And because there are long chains here, big molecules, they may have also induce some issues related to injectivity and reduction in permeability that we're going to talk about. So these are some of the issues with polymers. All right, so on the same aspects, these polymers can also adsorb to the rock, the reservoir rock. They may reduce the effective permeability, I talked about it, may reduce rock accessibility. I'll talk about this in more details, what I mean by that. Increase the injection pressure and may reduce the well injectivity overall. So these are if you like, they start to sound like the side effects from the COVID vaccine, right? There's too many things actually, but there is, again, there could be benefit from that. If none of this is observed, meaning none of these side effects, if you like, is observed in the field, most likely you're working with damaged polymer, meaning that your polymer that you're using in the reservoir is not affected. Okay, if you don't see anything of this. So, of course, here the challenge is to keep the balance here, right? You don't want to have very low injectivity because this will kill the project. At the same time, you don't want to use ineffective polymer where you don't see any of this, where eventually it doesn't help you in improving your oil recovery. All right, so this is in some of the mechanisms that I talked about in this illustration. These are the polymer molecules at the pore scale that we're looking here. As you see, they can adsorb to the grains. They can tangle with each other. They can clog some of the pores here. And you see here when I mentioned the inaccessible pore volume. So as these polymer molecules clog, they may plug some of the pore throats, and they cannot go through. They are larger than the pore throat. They're too large to go through some of the pore throats there. While water can still be able to go through, pass by. Okay, so in this case, it behaves like a filter here, okay, for water. And here, of course, the adsorption, it has also complicated form of adsorption. It could be maybe multi-layer adsorption, entanglement, and so on. Okay, for it. Now, with this interaction with the rock, complex interaction with the rock, comes also some challenges or some observation that we see even at the in the field or even on the experiments when we start to inject polymers. This is an experiment here where polymer is injected in a long sand pack, and we see here the adsorption happening within the sand here. Typically, you have higher adsorption toward the injector or the inlet, and lower adsorption toward the outlet. This reflects this additional retention of polymer on the top of the typical adsorption. And on that, we can see also the effect of, this is the injectivity, PSI per foot. If you start to inject polymer, of course, in some situation, right? I'm not generalizing that this is happening all the time, but in some situation where, some of the, conditions don't fit really well to that particular polymer, you start to get reduction in injectivity. Right, so meaning that you need more pressure to inject that volume, and this is over time or over pore volume injection. You start to see this is like continuous drop in injectivity. Okay, for it, and we observe this in the field as well. Now, on the other side, if you try to flush this the polymer, the sand pack with water, for example, to flush the polymer out, you cannot easily displace all this polymer out. This is, for example, from right here. They show that if you start to push the polymer out, and this is reflected by what we call the residual resistance factor. I'll talk about it. Okay, this reflects how much polymer is still retained in the system after you start to inject water in it. So you can see here, for example, after 10 pore volumes of water, you still have some polymer still coming out of the system. Even after 100 pore volume, you still have some polymer left in the system there. It's hard to displace now. Now, with all this, again, complex relationship with the rock, polymer, and log, there's also other effects that we call I showed you about the inaccessible pore volume. And this is really a very complex mechanism because the polymer may not be, as I described before, may not be able to go through some pore throats while water can go through. Okay, and this with this effect, it creates some sort of segregation between polymer molecules and other smaller molecules, like for example salt molecules or tracer molecules and so on. Okay, for it. And this has been observed in the lab by putting a tracer and polymer, and you see the segregation or the separation between these molecules. So this has been calculated and recognized in the past. And what we know that typically the inaccessible pore volume is something between 5 and 30%. So meaning that, in other words, if you inject this polymer, the polymer molecule may not be able to access about 5 to 30% of the pore volume of your rock. Okay, for it. And so some of the work that we did here at KAUST, we tried to visualize this mechanism, right? We look at different technologies. One of them is the microfluidics. And with that, we also use some advanced imaging technology using single molecule microscopy, where we've been able actually to tag even the molecule, the polymer molecule, okay, and observe what happens there. So this is a system that we created with different pore throats here, or different, if you like, channels mimicking different pore throats, okay, in the rock. So this is one example, and this is from another experiment here, but for the same concept, right? To see, you see here we created different pore throat sizes versus meaning fine and coarse one, and put polymers. So we did observe the clogging of the polymer, and for that experiment that I showed before, we have here animation, actually a video. Let me see if I can run this. Yes. So here you see the highlighted here particles. These are the polymer particles or polymer molecules, tagged molecules, and you see here the red reflects the clustering or the agglomerate of these polymers. And they, as they flow, you can see here they can clog some of the pore throats. And in some situations here, for example, they may get stuck on some location, and then after that, as the flow changes or other, something, change in the surrounding, these molecules may get freed and then may start to flow again. So we see this effect of clogging and unclogging, and this reflects some sort of reversibility of this process as well. We also did this experiment at the larger scale. We put sand pack here, mimicking different rock configurations or rock property like fine sand and coarse sand. And we would injector from one side and production from the other side, and see the effect of polymers. And this is also another experiment where you see here first we did water flood. You inject from this side, produce from this side, as expected, water will just shoot through this high perm layer or high zone layer here. Okay, for it. And if you would put polymer, okay, you see here that polymer will have less tendency to go through these high perm channels compared to the water flood. And this reflects what I mentioned before about the improvement in sweep efficiency. Of course, you can do simulation as well here just to replicate these experiments, okay, as you can put in the simulator. And then you can run other conditions where you can play with the wettability and also the injection rate to mimic what we call imbibition mechanism. And in some situation, actually, you can even set the system so that the polymer will almost completely avoid going through the high perm channel. Even though this channel, the permeability of this channel could be maybe 3 orders or at least 2 orders of magnitude higher than this one. And you can still do that. Okay, for it. All right. So a bit more also on some of the mechanisms of the polymers is back to the what I mentioned before about the injectivity or loss of injectivity. This is captured with a parameter called the resistance factor, and also another parameter called the residual resistance factor. So let me explain very briefly what these factors are about. So let's say you have, this is your core, and you're injecting here. You want to inject, for example, a given rate, okay? And for that, you need to have a given pressure drop across that core, let's say. You have delta P. If you would do the same thing now with polymer, right? Say you want to inject the same rate, then you need to have higher pressure drop, right? You need more pressure to inject the same volume simply because the polymer is more viscous, okay? Now the question is, after you inject the polymer, you're done with it, you go back and inject water. Do you go back to the initial state here, okay, for your delta P? And what we notice here in the literature is that there is really ambiguity around this, all right? So meaning that you may not be able to go back to your the initial injectivity, okay? But the process is a bit dynamic there. So there is, there is some sort of partial reversibility of the process, okay, which complicates the system. Now, this is not very well, if you like, established in the literature and created some confusion. Okay, so let me explain what the confusion is about. The irreducible or the residual resistance factor. Let me go back to this. This factor here, okay, it behaves as if when you go back to the water flood, okay, after polymer flood, if you keep the same resistance factor as before, this means that as if now your water has lower mobility. And this is reflected by the relative permeability here. So in other words, okay, let me put it in this way. If you start, let's say, before polymer flood, your rel perm will be something like this. This is the end point, the KRW, right? And after polymer, so water flood after polymer, your rel perm will be somewhere here. So what does this mean? It means that now your water, as if now your water has lower mobility, which is also equivalent as if now your water has higher viscosity. And with that, actually, people in the literature, they start to, optimize, or they start to plan their polymer flood so that they do polymer, small slug of polymer followed up by slug of water here to save, to use less polymer here. They do, water flood, or what we call the chase water here, and they count on this, irreversible effect of polymer by reducing the water mobility. Okay, I'm not sure if this is very clear, but this is sort of a trick that people try to use, okay, taking advantage of this irreversible effect of polymer. Okay. Now, our observation here in the lab that this is not true, meaning that because the irreversibility is not permanent, you start to lose, you have some sort of partial irreversibility, so meaning that you have some reversibility of the process. Okay, so the polymer, meaning that once you start to inject polymer, you chase it with water, you start to lose the effect of polymer soon after that. And we did this experiment, and we could actually show it, I will not actually spend too much time on it, but the bottom line here, there is a reversibility in the process. And this is also what we observed in the microfluidic system, where we injected, polymer, and we observed that polymer doesn't stick there forever. You start to displace it with after that. Okay, for it. And with this, it has significant implication, right? By assuming that process, is it reversible or irreversible? It has significant effect on the planning of your pilots, and so on for it, because again, if you assume irreversibility, you're overestimating the effect of polymer. Okay, for it. So this is the bottom line. And this is an example from a simulation here that shows with the traditional approach where you assume irreversibility and you do chase water after that, you have here the colored zone here. This is shows you the efficiency, displacement or the sweep efficiency of your chase water here. It's able to access all this region. While if you assume the reversibility, meaning that you're losing some effect of the polymer, you see that the system now is much less efficient compared to this one. Okay, so the bottom here line here is be careful of this fake effect of polymer. That is not actually true in many cases. All right, so this is a summary slide, all right, to show basic what are the different aspects of polymer. So there is very delicate selection optimization that need to be done for polymer. From one side, you need to use the high molecular weight polymers because you save on the concentration. All right, so in other words, with the same concentration of two polymers, one at high molecular weight and one at low molecular weight, same concentration, the high molecular weight will give you higher viscosity. Okay, so we try to reduce concentration by using high molecular weight. Okay, and in this case, so high molecular weight give you higher viscosity, lower usage in terms of mass. Okay, but on the other side, it gives higher risk because now it is larger molecule, is more it is more sensitive now to temperature, to hardness, to degradation, and so on. On this other hand, you have low molecular weight molecules. They give you less viscosity, so meaning that you need to use more mass, more concentration, but they're lower risk. And you see here the balance between the two. Typical concentration need to be somewhere, this is use concentration, somewhere between 1000 and 2000 ppm. Higher than that typically is not going to work much, especially from the economic point of view. And you need to plan for the polymer size. So this is sort of rule of thumb, doesn't work all the time, but roughly you need to have an understanding about the rock property, like the pore throat size, distribution, and so on, and select the polymer molecule to be much smaller. Okay, the pore throat size, because you need to make sure that this polymer molecule can go through this pore throats. You need to do core flood at the reservoir conditions and make sure that you include the low permeability and the high permeability rocks. Okay, not to be biased there. And you need to have enough pore volumes to measure resistance factor, permeability reduction, residual resistance factor, inaccessible pore volume, and retention at least 25 pore volume. So when you take the core, you inject polymer. You don't inject 1 or 2 pore volumes and say, all right, great, I'm done. You need really to inject for longer, pore volume to see the, the long-term effect of polymers. And this is, by the way, many times created some failures, even field failures because of this. Okay. You need also to measure the polymer stability, especially for temperature and salinity effect, and you need to age this polymer at least for 6 months. So you put it in the oven and see the stability of this polymer for, by aging this polymer at that temperature. Because eventually this polymer will go into your reservoir, and you need to make sure that this polymer will stay effective over the time, the residence time, all right, on it. And field assessment, and on top of that, you need to do water flood performance. Before using the polymer, you need to make sure that you have an efficient water flood from assessing the sweep efficiency, conformance control, balancing the patterns, and so on. And at the last stage comes the pilot. This is where you can go and test this polymer in the field. You need to carefully pick the pattern where you need to use this polymer. Don't go to the low performance or low quality wells, because it's not going to work. This is the recipe of failure. We've seen it all the time. And this is what the challenge, right, where it happens actually between if you go and design for the pilot, from one side you want to go and test the technology in the field. Typically there are going to be some debate there, right, between people on the field that they will not give you the best zone in the reservoir, right, because fearing that you may create any damage or impacting the overall productivity. So they will prefer to give you somewhere in the flanks or the corners or low, maybe performing wells there. If you go there, it's gonna be guarantee a failure, all right? Because if the water flood doesn't work well, polymer will not work well either. Okay, so be careful about that. You need to plan for at least one pore volume to inject, and it requires a lot of patience. So one pore volume, it may take actually 1 to 2 years in a pilot to inject. All right, and you need to wait maybe around 0.4 pore volume to start to see effect of the polymer. So in other words, if you put a pilot, you may need to wait maybe 4 to 6 months to see effect. Okay, you're injecting these chemicals, no effect. Hopefully in 6 months you start to see something. So it requires patience here, and of course on top of that you need to have very careful planning by doing careful modeling and simulation and so on. So as conclusion on this, polymer flood could be a value-adding EOR. It could be combined with other technologies like low salinity flood and so on. Some models in the literature could be misleading, and this is from our field observation. All right, for it. So you need to be careful with that. It requires high resolution simulation. You need to have really a rigorous roadmap to be very careful in testing it. And of course, you need to get back to the fundamentals all the time, right? Understanding all these mechanisms, how they operate, even at the pore scale, the micro scale all the way to the macro scale, understand the effect of this heterogeneity. Because if you do this randomly, most of the time, if you don't have very careful planning, these pilots or this technology will fail. All right, with that. All right, and of course, with all that, I would like to thank all my collaborators, my students, from Antonia, Abdullah, Amir, Sean, Ahmed, Victor, who did a really excellent job and still working on this area. And also, I'd like to thank my collaborators here at KAUST. And with that, I'll thank you very much, and hopefully I didn't take too much of your time, and be happy to take any other questions. Thank you.
Thank you so much, Professor Hussein. It was very insightful. Thank you so much. Before we move on to the question and answers session, I would like to announce that we will have a group photo, so please get ready for that. And yeah, if you have any questions, so please go ahead. You can open your mic or you can write in the chat.
Thank you, Professor Hussein. It was very interesting and informative. I would like to present to you this certificate as an appreciation from us. Please accept it and will be sending to you.
Great. Thank you very much. Very, very appreciated, Mohammed. Thanks. Ali. Right.
If anyone has any questions, you can write in the chat or you can raise your hand if you would like to speak, please. There's a question in the chat if you want me to read it.
Okay, let me try to see. I'm going through the chat right now. Okay, so okay, so I have a question here. It's saying, is it possible to find a method to stop or slow the formation of polymers? All right. Okay, so I'm not sure if I got this question very clearly, but let me, I think there is some important aspect of it. Thank you for the question. All right, so polymers, I showed you this, like the HPAM polymers, right? These polymers, they come as a powder, and then you mix them with water, okay? And then in the process, you start to hydrate these molecules, and they start to stretch, right, for it. So they require some sort of, initially some aging time for these polymers to get fully established, okay? Typically here in the field, we don't, when you take this, this powder, you mix it with water, it goes to different mixing steps, mixing stages, and requires at least maybe sometimes 6 months, 6 hours to do so, okay, in the mixing process. So this is part of the complexity, right, of dealing with polymers. At the same time, when these molecules or polymers are fully established, the molecules, you cannot actually use just regular pumps to inject them. They require low shear pumps to be able to inject them without damaging these polymers. Now, there's now people working on before actually having the full establishment of this of the polymer at the surface, you can you inject these polymers before they are fully hydrolyzed. Okay, so they are not fully established, and in this case, you may they are lower, so they can provide. They are not at their full potential. Let me put it in this way. They're not at their full potential to establish that viscosity, the high viscous fluid. And once you inject them and they get to the reservoir, this is where they get, stretch and they start to gain viscosity. So there is something, some work in this area and in different places. They're trying to establish these polymers. And from one side, they're useful, okay, for EOR purpose. So in other words, if I want to simplify this, you're injecting this polymer, you're injecting it as low viscous fluid, and when it gets to the reservoir, it's enough time there and start to establish and build up its viscosity. Okay, so with this, you avoid maybe damaging the near wellbore area, because these polymers now they can pass easier, okay, from around the wellbore. At the same time, these type of polymers are useful for other applications, like what we call conformance control. In many situations, you have these thief layers, right, and high perm layers that are high conductive channels for water. Okay, and when you inject water, water go through these channels and create air breakthrough. So some of these polymers now they are used. You inject these polymers, and sometimes they may need another chemical to them. They're called like the activator, all right, where you inject the polymer, you inject another slug of chemicals, and then when these chemicals mix together, you create this gelation in the reservoir. Okay, and you start, of course, here you're targeting these specific channels for it. Now, we don't, back to your question, we don't actually inject this gel or polymer from the surface, because it's going to be really hard to inject it. Once this polymer is fully established and fully gelated, it's hard to inject. Okay, so this is why we try to inject it while it is low viscous, and when it gets to the target zone, hopefully, this is where it start to get the gelation and start to get activated there. So hopefully this answers some of maybe the question that you asked there, All right. Any other questions?
Yes, excuse me.
Yes, go ahead.
Yeah, so this is Yusuf Hamad. So it's from the simulation run that you showed us, it seems that Polymer Flood does improve oil recovery quite considerably, but it's still uncommon in the world to use. And I'm assuming it's because of costs eventually. You mentioned that in the US, they do give them tax breaks for using Polymer Flood. But when it comes to Polymer Floods, what is the most expensive component in it? Is it the powder? Is it the surface facilities to inject? Or what would it take to actually bring the cost down such that it's more viable or economically feasible to use?
All right. Thank you, Yusuf. Excellent question. All right. There's many aspects to it. All right. So first of all, let me put it in this way. Nobody will use polymers, all right, if the water flood is working well. Okay, if you can produce your oil efficiently with even primary depletion or water flood, nobody will use and you go and use polymers, right? So it's not really fun, right, in using polymers. This is hard to use. But in many places, right, you have to use polymers or others, right, other chemical EOR or gases and so on. it is just out of sort of, let me put it, maybe desperation here, because you cannot do primary depletion. You cannot do water flood because water flood is not effective. So you have to use two options here. Either you just shut down your asset, your facility, all right, or you go with this type of technologies. Okay. So all right. So once you decide that you have to do polymer, right? Now, what is the cost associated with polymer? All right, different things. From one side, we have the cost of the chemical itself. Right, the chemical, the polymer, I mentioned, roughly it's let's say $0.5 to $1 per pound, all right, for the cost of polymer. The other thing is also in terms of the transportation and logistics, where this polymer is coming from. Do you have a local vendor, a local supplier for this polymer? Let's say if you're, operating, in the Gulf region. Where is this polymer will be coming from? Is it coming from China or coming from Europe, or you have local, supplier for it? So the cost of transportation makes big difference. The other thing is your field onshore or offshore? Onshore, you can actually manage to get the polymers by trucks. You can, if you also, sometimes it is challenging depending if you have easy access to the field, you have enough roads there, and doesn't create issues in the traffic and so on. This is onshore. Offshore, it is a challenge now. If it is offshore, then dealing with powders is tricky because of transportation. So you need maybe, in this case, you have to consider other type of polymers, like, that comes in the form of emulsion. So it comes like a, sort of, liquid form, okay? And you have to deal with it. It creates some other issues, when it comes in this form. So transportation is a very big issue. Now, when it comes after that, you have the facilities you need to have on the surface. The polymers you need to from one side, you need now storage facilities. You need to have mixing facility. So I talked briefly about it. When you get the polymer will go to the powder stage or powder state, to different stages of mixing. Okay, you mix it with water at different stages to optimize the mixing process. You need to be very careful in the mixing. If you put it in just, a high shear mixer, is gonna actually damage the whole polymer. You kill the polymers. Okay, so you need to be very careful in doing that. So it goes maybe sometimes with 2 or 3 or sometimes 6 stages of mixing. And then you have a stream that goes from the polymer, so high concentrated polymer, and goes actually and join the water flood, pipeline. Okay, so this is in terms of the facility. So you need to have all this in place, right, for it. So this is in terms of the cost related to the facilities. If you are offshore, this adds complexity because you may not have enough space, on your platform, to do all this. So sometimes everything is great, everything looks perfect polymer, but you don't have maybe the the surface facility that is designed, to have this type of equipment they needed for polymer mixing and so on. This is and then when it gets to the I mentioned you need to have different type of pumps. The ones that you simply use for water injection, they will not work for polymers. You need to have larger, lower shear pumps, more expensive. Also, when it gets to the wells, it's not. You may not be always possible to use the water injector. The ones that you use for, you start with for polymers. Many times you need to drill the new wells, okay, for it. And also the other aspects relate to the number of wells, right? So with water, for example, you can put large well spacing. You don't care, right? You're injecting from one side, doesn't matter the residence time, right, for your water in the reservoir. While polymer, it matters, right? As I mentioned, typically polymer is sensitive to temperature and sensitive to the water chemistry and so on. So it will a polymer molecule will lose effectiveness after some time. Okay, typically let's say 6 months, 1 year. So you cannot count on leaving this polymer molecule in the reservoir before it gets pushed out, right? More than say a year or so. Okay, so what does it mean? It means that your well spacing need to be smaller now, right? Because this will, which is actually reflects the residence time in the reservoir, right? When you put polymer, you push the fluid out, you need to produce from the other side. All that should happen within 6 months to 1 year, all right? So again, polymer meaning that, from one side, I need more wells related to the residence time. Polymer also, because of the injectivity will drop no matter what you do, right, compared to the water flood. And you need to inject fast, okay? So again, this reflects that you need more wells to it. So on brief here, there's different aspects to it. There is cost of the chemical, cost of the new wells that you need to drill, compared to the water flood. You have more wells to drill. And then you have to deal with all aspects of the logistics, getting the chemicals, the supplier, and so on. But again, I don't want you guys to sound that this is something impossible to do, right? There's many places, including, for example, I think in Oman, polymer is very commonly used there for many fields and many other places around the world. Okay, it's not sort of mission impossible. Hopefully I'm not sounding, too like pessimistic or so about this technology. It's just, this technology requires actually way more than what you typically do in water flood. But this is purely is a very, very mature technology, and people know how to do it very well. Okay, only. But just you need to be careful on all these aspects that I talked about. All right, great. Any other questions?
No questions, I guess.
Yeah.
All right.
If you can please turn on your camera so we can have a group photo. All right, everyone. Smile. Thank you, Professor Hussein.
All right. Thank you very much. And, hopefully next time probably we'll see you in person. Hope you think so.
You're more than welcome to join us.
Thank you again, and you're all also welcome to visit us at KAUST. I didn't get the chance to talk much about it, but, again, thank you very much for the invitation. Take care.
Thank you and have a good day.
You too. Thank you. Bye.
Take care. Stay safe. Bye.